Alright, Ms. Howard's chemistry class. This is part 4 of the notes on acids and bases, and we're talking about common acids and bases still. And we're going to focus on writing the chemical formulas of the acids and bases, and also we're going to understand and differentiate among acid-base reactions, precipitation reactions, and oxidation reduction reactions. We're going to focus on the acid-base reactions. Alright, so Roman numeral number 4, acid-base reactions. Those are also called neutralization reactions. And that's a reaction in which an acid and a base react in aqueous or aqueous solution to produce a salt and water. So they have to be in liquid form. You put an acid, you combine it with a base, and there's a chemical reaction, and they're going to produce salt and water, salt water. However, don't get too happy with saying it's salt water, because a lot of times we get stuck in our heads salt is NaCl. That's not the only salt there is. So here we have an example. This is the one that actually does produce sodium chloride. We have hydrochloric acid plus sodium hydroxide, and we're going to produce sodium chloride and water. See the little AQ on there? That AQ just means, hey, it's got to happen in aqueous solution. And then the L beside the water means water is a pure liquid, so we don't say it's dissolved in water. You know, how can water be dissolved in water? Kind of crazy to say that. All right, so again, we have an acid plus a base, and we get a salt plus water. That's what the neutralization reaction is called. So it doesn't necessarily mean that the acid and the base will completely neutralize each other, so you have a perfect pH of 7. It just means that that's the name somebody gave them. Those reactions of acids and bases, that's just the name they gave them. Right, so you have the hydrochloric acid and sodium hydroxide. Now what if we put a different acid with the sodium hydroxide? We have acetic acid, which is vinegar, HC2H3O2, plus the sodium hydroxide. And again, see the double replacement reaction? The sodium and the first hydrogen swap places. So we have a double replacement reaction. So the H is with the OH now, so we have HOH or water. And then the Na is with that C2H3O2, so we have a new salt there. That salt happens to be sodium acetate. Salts can be neutral then, they can be acidic, or they can be basic. Now look at this second reaction right there. We have sodium hydroxide, which is a really strong base, and then we have vinegar, which is a really weak acid. So you have a strong base and a weak acid, and you're going to form the salt and water, but do you think that your products, your salt, do you think it'll be more basic or more acidic? Strong base, weak acid? It makes sense that it's going to be more basic. So that NaC2H3O2 salt, if you tested the pH for it, it would be above 7. It would be a basic salt. So we have a strong, and we end up getting neutral stuff. So that's your first reaction. We have a weak and a strong, and we end up getting a basic salt. So salts can be neutral, acidic, or basic. And remember, neutralization does not mean that your final pH ends up as this perfect little neutral 7. It's just a name that they created to talk about the reaction between acid and base. So neutralization doesn't mean that you've got a pH of 7. Alright, so again, acid plus base yields water and salt. There are lots of everyday uses that we have for this. If you have indigestion, your stomach hurts because you ate something that didn't agree with you, a lot of times it's going to be indigestion. And that means your body's kicking out a lot of acid, a little bit more acid than maybe it needs. And so, you know, on the inside of your stomach, you've got that nice thick layer of mucus. And a lot of times it can burn away that mucus. You're making so much acid and cause some problems there. And touch the, if you have the acid touching the lining of the stomach wall, that's not too great. So in many cases, we take antacids, and those antacids neutralize or work on neutralizing the acid that's in your stomach. So if you have acid in your stomach, you put a weak base with it, and you can neutralize some of that acid. Farmers actually put an acid or a base on the soil to control the pH. My husband decided one summer he wanted to grow blueberries. And he found out that blueberries required a different soil type than what we had. And he ended up having to put some acid on the soil. It might have been base, I can't remember which one. But he ended up having to put some stuff on the soil to change the pH of it. Otherwise, he couldn't grow the blueberries at all. You have acid-base reactions that actually create those formations of the cave stalactites. Remember the things coming down from the ceiling? That chemical that's in the ceiling there, that's a salt. And so when you have some acid rain, maybe that's percolating down through the basic soil, you get those salts produced. And that's what those stalactites are. Oh, kidney stones. You guys have probably heard about people having kidney stones, and they're not pleasant at all. The human body, kidney stones form from insoluble. Insoluble means they won't dissolve in water, salts. So some people have a tendency to develop these kidney stones. Some people don't. Thank goodness, not everyone does. But those are actually, when you urinate them out, when they finally kind of scrape their way through, they're little bitty tiny rocks that look, that are made of a salt of some type. Usually a calcium something, but not always. A lot of times they'll take those little rocks that you urinated out that isn't going to feel too good coming out of your body, and they test those and see what chemical they're made of, and they kind of tell you, hey, you need to stay away from these foods because this is the chemicals that are causing those kidney stones in your body. All right, bases neutralize acids. Milk of magnesia, huge magnesium hydroxide, and it neutralizes your stomach acid. Oh, look, it says on the bottle it's even a laxative for you. So we have HCl plus MgOH2, and you get the salt, MgCl2, that's magnesium chloride, and water. So again, you have an acid and a base, and you get a salt and you get water. Now, is magnesium chloride, is it poisonous to you? Well, probably not, since you're taking this medicine, and that's going to be one of the byproducts that's made from it. So, it's not going to be poisonous to you in that sense. Oh, what about bug bites, bee stings, ant bites, wasp stings, and stuff? Some of them are basic, and some of them are acidic. Wasp stings have a base in them. So in order to get them to quit stinging so much, you have to neutralize them with something opposite of that, and that's an acid. So sometimes they'll say put vinegar or lemon juice on the wasp stings. And you kind of have to know what it is you're talking about. If you put vinegar on something and it makes it hurt worse, get it off there. Ant bites are with an acid, red ant bites are with an acid, and in order to neutralize them, you're going to have to put some kind of base on it. So a lot of times they'll say make a paste out of baking soda and put that on there, and that'll make it feel a little bit better. So acids neutralize bases. Again, we have the acid plus the base, and we get the salt and we get the water. Neutralization reactions always produce a salt and water. Always. So if I say, hey, here's one side of the reaction, these two things are reacting together, and one's an acid and one's a base, one of the products absolutely is going to be water. And then you can figure out what the other one is. So again, it's also kind of good because they're just, in most cases, they're just simple double replacement reactions. Double replacement reactions are easy. You swap the first two things, and then you look on your ion chart and see, well, how many of the H's do I have, how many of the OH's do I have, and so on. Now, if you want to make something produce a neutral salt, you have to have the exact amount of acid and the exact amount of base. And so you have to calculate that. Yes, I said calculate. Alright, so there are lots of interesting things about salts. Here are some common salts that you have there. We have sodium chloride, we have sodium nitrate, sodium bicarbonate, that's your baking soda, potassium carbonate, and then you have ammonium chloride, which is a weird name. It's called sal ammoniac. So there are some common salts that you have. And what's really cool is that picture up in the right-hand corner. That picture is of sodium chloride, and that's just one little crystal. It's a nice little cube. Alright, so salts are ionic compounds containing a positive ion other than the hydrogen and a negative ion other than the hydroxide. So typically it's a metal and a non-metal. Okay, so what we're doing is we're saying, hey, it can't be hydrogen and it can't be the hydroxide ion. So it's a metal and a non-metal that are bonded together. Usually the metal comes from the base and the non-metal comes from the acid. Under what conditions do salts conduct electricity? Well, you put them in water and they're going to conduct electricity. Oh, my arrow's messed up. Sorry about that. So as long as they're aqueous or aqueous, put them in water and they're going to conduct electricity. Salts are just glorious.